Okay, hi everybody, it's Dr. B here, and it is now week 3 for Organic Chemistry Lab. This is a little pre-recording that I'm going to do that I'll go ahead and post before our actual session, and it will in many cases be very similar to the actual recording that we'll do at 6:30 that will include all of the input from 20 students as well. So here's what we're going to go over today. We'll begin by recording it on the Zoom session. We'll take attendance. We'll review last week, particularly the quiz. Scores could have been higher on that quiz. We'll take a look at what is due when, recrystallization, both theory and in practice. We'll watch the entire 18-minute video, not in this pre-recording, I don't think, but in the regular session we'll watch it and we'll pause it and evaluate it. I'm looking for a lot of input from students when we do that. At that point, you'll receive your own fake data, which you'll use to write your lab reports. Focus on the 3 different methods of recrystallization that were used and evaluate which method is working best for you, and most importantly, why that might be. The underpinnings of the advantages and the disadvantages of each method, hopefully evaluating it on a molecular level. I will then go over all those files that you should have looked at before you began this lab and the course materials to make sure everybody's good on that. The most important one, I think, is the sample lab report. That's probably the best thing you can use to model your lab report after Professor writes it so that you get some nice high scores. That plus, of course, the scoring guide, the rubric. We'll talk about what's due next week, and there you go. So I will record, I will take attendance. And in terms of what's due when, it's pretty straightforward. The recrystallization pre-lab questions, there were just 2 of them. They were due at 6:30. We'll always have the pre-lab questions due just before lab, just like we did when we met in real life, when people would walk in, staple their lab reports together, say good evening to me, and that sort of thing. We're doing the same thing in a virtual sense now. We'll then the lab report itself is not due for 7 days, but it'll be due before the next class. The pre-lab questions will also be due then, and the second lab report will be due the following week. And that's the general pattern we'll follow. There'll be lots of exceptions for holidays, for multi-week labs, things like that, so watch your syllabus carefully, but that's the general protocol. Okay, so that does not look like we are there. We've just taken the attendance. Oh yeah, we've gone over what's due when. It's time now to talk about recrystallization in theory. So this is a slide that I created last several years ago for my IB class, and I can see that the images won't load. Isn't that interesting? I think I'll just keep rolling here so that we don't have to start the video over. Maybe I'll pause it and fix it, so bear with me. Okay, I've prepared this slide, and here's the theory of recrystallizations. You start with an impure solid, and this looks very impure. We want to end up with something like this, so we need to remove this colored impurity. So you take your impure crystal, or that solid. It might be amorphous or crystalline. Crystalline makes things easier. It usually is an indicator that your impurity is a very small amount. And by the way, this method typically only works if things are pretty clean to begin with. It's not something you can do with, say, a lump of dirt and separate it into pure substances. But you've got your pure stuff with something occluded within it, meaning that it is not part of the molecule, it's a separate substance. We want to remove that. To do that, we're going to heat it up and get it all to go into solution, at which point 2 possible things can happen. Either your stuff goes into solution and the impurity doesn't, which you see here, or your material will go into solution, as will the brown stuff, but then when you cool it, only your crystals come out. That's awesome. When that happens, you then collect it and you have your product. So you need to supersaturate it, meaning we need to heat it up to the point where it's oversaturated. There's a ton of product in there. The reason you do that is because it's easy to dissolve something, but it's hard to precipitate it back out. The only way you can do so for sure is to have a ton of your solid in there. Keep your solvent to a minimum. If you've ever made rock candy, you know that's the case. You use almost more sugar than you do water, and when you cool it, you are guaranteed to get your crystals back. If you overwhelmed it with water, you wouldn't get any crystals at all when you cool it down. So you always, and this is the most common error, you got to keep your solvent to a minimum. Then at this point, you have separation, whether it's in this form or this form. Your product has separated out, so you've accomplished your mission, but you need your pure stuff now. Once you cool it down, you'll collect your product. Sometimes you won't. The process of nucleation, where that first crystal forms, can be unpredictable. You may have to add one tiny crystal to it. You might have to scratch the test tube, but one way or another, you want to get that solid to form. Once it does, it's now separated. You have two separate things. You can just remove that by filtration. Since this product is now soluble, this impurity is now soluble and your product is not, you can go ahead and collect it by filtration and you have your clean product. And I show it stacked up like that because in my mind's eye, and I think it closely reflects reality, the first crystal forms and then the other ones stack on top of it like poker chips, if you will, and you end up with nice, beautiful crystals. It's a method that's still used industrially. It's used all the time, small scale. It requires almost no expensive gear, works great, and can give really pure substances. Let me go over some of this vocab here because I think it shows up. If something is amorphous, and I don't know if this one is, does this have crystals? This might be amorphous. That's an impure solid. It means amorphous, without shape. That's always a bad sign for recrystallization. It means it's harder to do. It's crystallization, not recrystallizations. You're not turning crystals into crystals if it starts out as amorphous. Supersaturation means if your substance is soluble 5 grams per mil, you've got 6 or 7 grams in there, say. You know it will precipitate out as soon as you can get that nucleation process to begin. That's when the first crystal forms. It can be either homogeneous, meaning you didn't add a seed crystal, and this is annoying. I don't think I can get away from that thing. I'll just try not to be in that area. That's spontaneous crystallization, and heterogeneous nucleation means you added a seed crystal. That is the theory of recrystallization. We're going to be recrystallizing benzoic acid, so now we'll talk more about in practice. Now, another professor added these things. There's a lot of writing in it, but I think I'll read it each time and we'll analyze it. It's always good to get somebody else's point of view. Benzoic acid looks like this. I think it's early in the year, so you may not be comfortable with functional groups, things like that, but when you see something that looks like water, OH, that means it's a polar substance and will probably dissolve in other polar solvents. And so the idea is that like dissolves like. See how that OH might remind you of HOH, which is water? That means this substance might require quite a polar solvent to recrystallize it from, and in fact we'll be recrystallizing it from water. So it's the primary method used to purify non-volatile organic solids. Non-volatile meaning if it just boiled off, well then you'd have a problem, right? I have last week's quiz here, not sure why. Okay, and here it is. So what factors make for a successful recrystallization? It helps if the impurity is definitely a minor component. We alluded to that earlier. It helps that if it's very soluble, more soluble than your material, it'll just dissolve and your stuff won't. Or completely insoluble, like pieces of rock kind of thing. That would also work. But if you do that, you've got to filter it off before you recrystallize, or you've accomplished nothing. So you try to use the idea of like dissolves like. You try to make a supersaturated solution. And here he shows it quantitatively, which I think is kind of cool. If benzoic acid at 20 degrees only dissolves less than 1 gram for every 100 grams of solvent, and you heat it up to 100 degrees and you get it up to 6.8 degrees, well, that's good numbers, right? That means when you cool it back down, you will lose a tiny bit. And this is not a quantitative method. You're not going to get perfect yields, but it should give you the vast majority of it back when you cool it out. And it helps if the impurity stays soluble even at room temperature. So that's the basic idea. In practice, you try a few solvents, see how it works, and off you go. And there's a little bit more that he has to say there. I think I'll move on. Water is a good recrystallizing solvent because it doesn't react and synthesize new substances. That's always nice, right? You don't want to have a chemical reaction occur when you're going to recrystallize. It's easy to filter off, it's inexpensive, it's non-toxic, and it's non-flammable. It's all true. Let's see. Looking at the effect of using two different isolation methods, actually we'll be trying three and we'll compare each one of them. We'll do regular vacuum filtration, we'll centrifuge off the solvent, and we'll also use water and methanol water as a combination. So those to me are really three different methods. Water recrystallization, water methanol recrystallization, and centrifugation is an added step to it. So this is your classic way to collect your material by vacuum filtration. I mean, if you're familiar with a coffee filter, you know that you just drip in your stuff and what dissolves goes right through. What does not get stuck in the filter paper. That's a good method, but God, is it slow, and so scientists apply a small vacuum to it so that normally what would take minutes can take place in seconds with a vacuum filtration device. The will filter goes on top here, and the idea is that the solid stays on top and all the water gets spun out, and that way you end up with just your solid up there. It's a very unusual, if you ask me, very rare method to use, but you can use this. And the advantage is that you can spin out the water instead of having to run it through. Funny things can sometimes happen when you run this through. If it's cooling, things might start to crystallize while it's halfway there, things like that. So the summary is that you identify appropriate solvent, either water or methanol water in this case. You dissolve the impurities in a minimum and a maximum temperature of solvent. So you boil it up in that stuff and then you let it cool. They say cooling slowly is best. Boy, it's hard in practice. So you want to try to let it cool slowly to get big crystals. And then once the crystals have formed mostly, you use an ice bath just to make sure you get all of it. You collect them. You can rinse them with a minimum amount of pure solvent, but that's dangerous because you might to redissolve some of your stuff. So people typically use ice cold solvent number one and number two a minimum. When you're writing your lab reports, if somebody did a classical recrystallization but the yield was low, maybe they rinsed it with too much recrystallizing solvent, or maybe they didn't use cold recrystallizing solvent. You then dry the crystals, and if it's in water, that takes days and is a very common issue that people weigh their crystals and it weighs more than it should, meaning it's just wet. So if any of you got 140% recovery, something like that, that would be a reasonable explanation. I don't think I want to read all his little details here. This is from another professor. He talks about little details. I'm going to let you read that, and when we get to the discussion section, why don't you ask me if any of this seems unusual? You weigh it out, and you weigh it out to 3 decimal places. So if it was 0.050 grams, that's 50 mgs, 50 milligrams right there. And that could be a good yield, right? Lots of more details from the professor that I'm not going to read. Percent recovery is important. So if you start with 50 milligrams, you'd like to recover 50 milligrams. If you only recovered 40, that would be an 80% recovery. Why won't you ever receive 100% recovery? Well, maybe you will if you're right. But if you have an impurity, by definition can't, right? Because that's part of your original mass. So that might be a good theory right there. Also, if you looked at that solubility data, it's never perfect. I don't know if there's ever a case where you'll get 0 grams of solubility at room temperature and all soluble when it's hot. So that's another factor, I think. More information here. And in practice, this is what's going on. You take your substance. This is what we really do in the lab. You'll watch Professor Wrights do this. You grab what we call a reaction tube, which is just a graduated test tube. You stick your impure stuff in there, use a minimum amount of water, and you heat it up. Now, this, I have to say, strikes me as a very poor tool for the job for 2 reasons. One, Look at all this surface area you got to deal with once your crystals form, and you got to try to get it off. It's usually better to have a container with a minimum amount of surface area so you're not scraping every square millimeter to get all your stuff out. And number two, this reminds me a bit of a gun barrel, meaning that when this stuff boils, if it pops, it'll shoot right out here and in that general direction, and that can be dangerous. That's called bumping, and it's a real concern. We don't tend to use for this device, what do they call this? Boiling chips. We use this boiling stick. A boiling stick is nice because it's so easy to remove. You just pull it out, whereas the boiling chip can be a pain to remove later. But when you watch the video, watch how concerned Professor Wrights is constantly, because he's done this for decades. Watch how concerned he is about where he's pointing this thing and the possibility of bumping. I think there's one point where he forgets the boiling stick for a second, and he says, "Oh, that could have been bad," and he's right. So, unusual method, but that's what we do. Here's a million steps that the professor talks about. I'm going to skip every one of them. And then in part two, you heat it up and you cool it. I think, oh yeah, look, all that is taking place. Heat it up, cool it, and you should get crystals, the impurity in this blue stuff. Now, you can remove most of the water with a pipette here or by will filter. And then it's time to collect it. Whoop, there it is. Once it's all cooled out, you collect it. And if you're using methanol water, which they do, it's just a different solvent system which may or may not work better. Methanol has CH3 in it. It's got a greasy component, so it's a little bit more of a greasy solvent system, meaning hydrophobic. Okay, here's where we are. We've done the recording, the attendance, all this, okay. And now it's time to watch the entire video. This will be 18 minutes long. I think I will click on it just to see if I'm hearing volume and to make sure that the link works. So I'm at 1650. When this thing goes through, I'll see what I get after this goes onto YouTube. So let me play. Whoa, I definitely hear that. I wonder if you can hear my voice over it. Okay, that should be enough to test the system. We're now going to get out of that and keep moving. I think that I can just go to the next slide. Here it is. So now you've watched the 18-minute video. It's time for your fake data. And I've got it set up for each one of you by name, so this should be pretty straightforward. Trying to click through this. There it is. So here's your names, and here's the data that you're given. So let's just take a look at Shannon's, for example. She's got number 7. The water vacuum filtration method gave 29 out of 51. That looks like a better than 50% recovery. The water will filter method looked horrible, gave lousy yield. And the methanol water method gave a lower yield than the vacuum filtration. But analyzing by melting point, that's a 0.2 degree range. Wow, that is tight. So high yield and amazing melting point data, method of choice. Here, 3 out of 52 is such a horrible method that I don't really care about this purity, and it's not as good as the other one. And here we've got less than a 50% yield and 1.6 degree range, or is it 2.6 degree range? So no brainer. By far, this is the method here. And we do have data that suggests that the recovery is okay, and the percent, the purity looks excellent. And then you talk about what might be responsible for losing all those 32 milligrams. Maybe it was all impurity. I kind of doubt it. You could try to talk about reasonable methods for why we lost so much of this stuff. Okay, so I'll just go back a little here. Look for your name. Should be able to go back. Going the wrong way. There it is. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. This is posted, so you don't have to write this down feverishly. All this data is available. I mean, take a picture if you want to. 1920. So that's the data for everybody, and we're just about done. Let's look at all the files. When I actually give the presentation, I'll go back, and I think I'll just make sure this works. We'll go back to see some of all the stuff you need. So for me, I go to my Blackboard page, and there it is. And I go to my course materials for this lab, and there they are. And there's lots of stuff. You can look at the syllabus here. We have week 3 here. So I hope you looked at all these links. This is incorporated into this presentation. The video is also incorporated. Modified directions are good to look at because that's what is really given for people to do. That's what you'd be following in the lab. So when you're explaining things in reality, you might want to take a look at that. This is about the same. The pre-lab assignment you should have already completed. And is there anything else? I don't think so. Course materials. We could go back. The introduction guidelines for, yes, for writing things in general, right? The most important document, I think, is this sample lab report. Did you see all those other things? You should be taking a look at everything. Now, I've been having trouble opening things lately, but if this opens, then this is probably the key piece of material. And you see that? I think it did not open. But when you take a look at that, that is Professor Wright's writing an exemplary lab report. Yours should look like that one. For details, consult all the other information. Okay, I think that's about enough for now. Let me see if there's anything that remains. I can do it this way. There's week 3. Let me just go down to the end of this fairly large document here, and we will call it a wrap. Probably looking at sample data down here once this loads up. There it is, sample data. Good, good, good. And is there anything else? I don't think so. We've covered everything. Be sure you know what's due next week, which is both the first lab report as well as the pre-lab. So just submit it to Blackboard before we begin, and you should be good to go. Okay, everybody, thanks a lot. I look forward to seeing you all at 6:30.